Hello everyone, welcome back. Today we are going to dive into an exciting and essential concept, the potential energy of a system of point charges. Now you may have heard about potential energy before, but when it comes to electric fields and charges, the concept takes on a whole new meaning. The potential energy is the energy possessed by a system of point charges by virtue of their being in an electric field. When charges are infinite distance apart, they do not interact and their potential energy is zero. If you want to assemble a charge system, that is bring all these charges near each other, work will have to be done. This work is stored in the form of potential energy in the system of these charges. In simple terms, the potential energy is the energy that a system of point charges possess due to their positions in an electric field. Let's start by considering 2-point charges. Consider charge Q1 placed at a specific point, say P1. The second charge Q2 is initially far away at some infinity. If we want to bring the charge Q2 closer to Q1, work has to be done. This work is stored in the form of a potential energy. This leads us to define potential energy as the system of point charges as the total amount of work done in bringing various point charges to their respective positions from infinitely large mutual separations. Let's break it down with some math. Suppose we have charge Q1 at position P1 with the position vector R1 in space. Let charge Q2 is initially be at infinity. We bring the charge Q2 to position P2 whose position vector is R2. And the distance between the charges Q1 and Q2 will be now R12. Consider another charge Q3 whose position is at P3 and whose position vector is R3. We'll consider this charge Q3 later on. The electric potential at point P2, this point P2, due to the charge Q1 at P1 is given by V2 is equal to 1 by 4 pi epsilon naught Q1 by R12. The work done to move the charge Q2 from infinity to the point P2 is simply the potential at P2 multiplied by the value Q2. So work done is equal to P2 into Q2. And this work is stored in the system of charges Q1 and Q2 in the form of potential energy U. U is equal to V2 into Q2. So which we can write it as Q1 Q2 by 4 pi epsilon naught R12. Now let's think about what happens when the charges interact. If the charges have same sign, this Q1 and Q2, if they are of same sign, both positive or both negative, the work done is against the repulsive force to bring them closer. This means the potential energy of the system increases as the charges move closer. On the other hand, if the charges are separated, the electric field does the work and the potential energy of the system decreases. So what we mean is Q1, Q2, if they are same sign, as we bring them closer, potential energy increases. Similarly, if Q2 and Q1 and Q2 are in different sign, the potential energy decreases. But this is a case when if the charges are made far away, the potential energy will be the opposite of it. Consider the three charges are present. Then what will be the potential energy? The total potential energy is the sum of potential energy contributions from each pair of charges. So for the charges Q1, Q2 and Q3, potential energy, total potential energy. Let me write it that. U due to Q1, Q2 plus U due to Q2, Q3, potential energy due to Q1. So how can we write this? 1 by 4 pi epsilon naught. I'll take 1 by 4 pi epsilon naught common. Q1, Q2 by R12 plus Q2, Q3 by R23 and Q1, Q3 by R13. As you can see, we add up the potential energy between each pair of charges, taking into account their distances. The same method can be extended to any number of charges in a system. So, this is for 3-point charges. Let's quickly discuss the potential energy of a dipole in a uniform electric field. The electric field due to this charge can be written as E is equal to 1 by 4 pi epsilon naught Q by R square. So from this we can write Q is equal to 4 pi epsilon naught R square into E. Now, we will be requiring this. The potential due to a dipole. We know that the potential due to a dipole is V is equal to P cos theta by 4 pi epsilon naught R square. The work done by this system can be written as V into the negative charge, which can be written as cos theta by 4 pi epsilon naught R square. We'll take this negative here, the Q. Substituting this to the key, Q, so can be written as R square into 4 pi epsilon naught R square E. We have the negative sign. Cancelling this part, we get minus PE cos theta. So the potential energy given by minus PE cos theta. Here P is the dipole moment, E is the electric field, theta is the angle between the dipole moment and the field. The negative sign indicates that the system's potential energy decreases when the dipole aligns with the electric field. To sum it up, the potential energy of a system of point charges depends on the charges themselves, their positions, and the distance between them. We use this concept to understand how energy is stored and transferred in electric fields, which is fundamental in fields like electromagnetism and electrostatics. If you enjoyed this video, don't forget to like, subscribe, and hit the bell icon for more physics content. See you in next video.